In this demonstration, you'll learn how to set up and solve a conjugate heat transfer problem in Ansys AIM. I'll demonstrate this using multiple physics regions to simulate convective heat transfer between a fluid and a solid. I'll use the fluid-solid heat transfer template. The geometry I'll use represents a steel manifold with air flowing through 3 inlets with various temperatures and velocities, exiting through a single outlet. The geometry includes both the solid and the flow volume, so I'll keep the default settings, create the simulation process, and import the geometry. Once the simulation process is created, I'll proceed to the mesh task. The template has already defined certain default settings and has also created some mesh controls. I've already applied inflation to the faces of the fluid body on the interior of the manifold. I'll update the mesh task to generate a computational mesh. In the physics task, the template has already created 2 physics regions, and you can easily add more if you need to. In this example, the template has created one for the fluid region with fluid flow and thermal physics type selected, and the other for the solid with thermal physics type selected. There are various settings for each region, and some require attention. I'll begin by setting up the fluid physics region and its associated boundary conditions. I'll select the internal fluid body, and using the context menu, I'll assign the selected body as the location for the fluid flow thermal physics region. I still see messages and indications that the task is conditionally up to date. That's because there are still some faces of this region that need to be assigned to a boundary condition or a region interface. For now, I'll proceed, and later I'll see the messages resolved. For the fluid flow region, I've already set up the associated boundary conditions. I've assigned these faces to be the inlet boundaries with different inlet velocities and temperatures, and I've assigned this face to be an outlet boundary. Next, I'll set up the solid physics region and its associated boundary conditions. I'll select the solid body, and using the context menu, I'll assign the selected body as the location for the thermal physics region. For the solid region, I've already set up the associated thermal boundary conditions. I've assigned these faces around the inlets and the outlet to be an insulated boundary, and I've assigned these external faces to be a convection boundary using the default walls expression to capture the relevant external faces. Working with multiple physics regions requires that a region interface be defined between any 2 physics regions. The template has already defined a region interface generator that, when generated, creates region interfaces between the fluid and the thermal regions. In this case, it will generate a single region interface object. I'll review the locations of the physics regions on each side of the region interface. For the first side of the region interface, the interface generator assigns all of the faces of the fluid region that correspond to the interior of the manifold. I can also see how portions of the model become visible or are hidden based on the selected region. For the second side of the region interface, the interface generator assigns all of the faces of this thermal region that correspond to the interior faces along the manifold. Now I can update the physics task to generate a solution. I'll keep the default solution settings as they are adequate for a converged solution. As the problem is solved, I can see the convergence of the residuals in the solution monitoring view. When the solution is complete and the task is up to date, I can review the results of the simulation. A contour result and a plane have already been created as part of the template. I've reused the contour result and changed its location to be the interior surfaces of the manifold instead of the plane. I've kept the variable set to temperature. I've updated the results so I can take a look at the changes in the temperature distribution on the interior of the manifold. I can also look at the temperature distribution along the exterior manifold walls. I've reused the contour result again and replaced the location using just the exterior surfaces of the manifold, keeping the variable as temperature. Upon updating the contour results, I can see the distribution of temperature along the exterior walls of the manifold. This concludes this demonstration of setting up and solving a conjugate heat transfer problem using Ansys AIM.